Okay, good afternoon, folks. This morning we went through all of the conceptual questions on the sample final exam. So this afternoon I'm making a separate recording to go through in detail all of the calculation questions that are on the sample final exam. So continuing from where we left off, which has us starting with problem number 13. At t equals 0, an electron is in the initial state. Chi naught is 1 over square root of 2, 1 minus 1, when a constant magnetic field B equals B along the y-axis that is pointed in the j unit vector direction. Find the spin state at a later time, chi of t, where t is equal to 5 pi over 4 times h bar over mu bb. And the problem notes that the Bohr magneton mu b is EH bar over 2nc. So this problem is about magnetic precession. When the spin of the electron is placed in the external magnetic field, that spin begins to precess. The Hamiltonian which governs the spin precession is H equals minus mu dot B. The magnetic moment is related to the spin by the gyromagnetic ratio, which is the charge minus E over 2mc times the G factor for the electron, which is approximately 2. Then you have the spin dot product of the external magnetic field. This object, if I put in G equals 2, is plus E over mc. The spin operator is H bar over 2. And if B is solely along the y-axis, then this is B times sigma y, just the particular Pauli matrix. This combination, not accidentally, EH bar over 2mc is equal to the Bohr magneton. So this object is mu b times B times the Pauli matrix sigma y. The exercise is then using this Hamiltonian to compute the time evolution. This is, of course, performed by the time evolution operator U of t, which is e to the minus I over h bar Hamiltonian times time, which for this particular Hamiltonian is e to the minus I mu b over h bar t times the Pauli matrix sigma y. So this has the form of Euler's formula, and we expand the exponentiation of the Pauli matrix as usual. This is cosine of mu b over h bar times t times the unit matrix 1 minus I times sine mu b over h bar times time times the Pauli matrix sigma y. Now I plug in the specific value for the time. This particular combination of time gives me mu b t over h bar is 5 pi over 4. That is exactly what I have here. So this is cosine 5 pi over 4 times the unit matrix minus I sine 5 pi over 4 times the Pauli matrix sigma y. Sine and cosine of 5 pi over 4 are both negative 1 over root. So this combination gives me, let me pull out the 1 over root 2, negative 1, 0, 0, negative 1. This is plus I over root 2. The Pauli matrix sigma y is 0, negative I, 0. So the combination together gives me 1 over root 2, negative 1 on the main diagonal, positive 1 in the upper right corner, negative 1 in the lower left. So this is my time evolution operator corresponding to that particular time, 5 pi over 4 h bar over mu bb. And so then finally I multiply the initial spinner. Phi of t is u of t times chi naught. And in this case, this is 1 over root 2, negative 1, negative 1, negative 1 times 1 over root 2, 1, negative 1. And when I multiply this out, I get 1/2. I multiply the upper element, I get negative 1, and another negative 1 is negative 2. And downstairs, I get negative 1 and positive 1, which is 0. So at the end of the day, I get the spinner after the rotation is negative 1, 0. So this particular spinner started off as an eigenstate of x, and after this particular amount of time, it has rotated, so now it is proportional to an eigenstate of sigma z. Okay, that was working through question number 13. Yes, looks good. Moving on now to question number 14. For a system with orbital angular momentum L equals 2 and spin S equals 1/2, apply the raising operator J plus to the angular momentum state LZ equals -1, SZ equals -1/2. This is an elementary building block of how one constructs the Fletch coordinate coefficients. You start with the ceiling or the floor, and then you apply the raising and lowering operator repeatedly to generate the rest of the ladder. So if you have a particular state that looks like this and you hit it with J plus, the key is to say J plus is equal to L plus plus S plus. Each one of these things has a particular operation on the state. So when J plus, or any angular momentum for that matter, acts on the state JZ, the eigenvalue is h bar square root of J plus 1 minus JZ. For J plus, it is JZ plus 1. Times the same state back, except raised by 1 unit in JZ. So this one is elementary to apply. I have J plus acting on the state LZ equals -1, SZ equals -1/2. So if I write this as L plus acting on the orbital piece plus S plus acting on the spin piece, L plus gives me h bar square root L times L plus 1. So L was 2, that is the magnitude quantum number. 2 times 2 plus 1 is 3. Minus LZ is -1 times -1 plus 1 is 0. Then this returns back the state where I've raised LZ by plus 1. So this gives me LZ equals 0, SZ equals -1/2. Plus, for the spin operation, I get h bar square root. This is a spin 1/2 object, so I get S times S plus 1, that is 1/2 times 3/2, minus SZ is -1/2 times -1/2 plus 1 is +1/2. And this returns back the state where SZ has been raised. LZ is -1, now SZ is +1. And so now I just simplify the expressions. Of course, the product of 0 is 0. And so I get h bar root 6 times LZ equals 0, SZ is -1/2. Plus h bar, this combination is 3/4 plus 1/4, and that gives me 1. So this is simply h bar, LZ equals -1, SZ equals +1/2. Okay, and that's the answer. This is the result that you get when I act on the state LZ equals -1, SZ equals -1/2 with the raising operator J plus. Okay, the next question is perturbation theory. Question number 15, you have a 3-level Hamiltonian system where the unperturbed Hamiltonian H0 on the combination of states psi1, psi2, psi3 returns back E minus 2E, and everything else is 0 times the states psi1, psi2, psi3 back. So these are the eigenstates of the unperturbed Hamiltonian with energies E, -E, and -2E. And the exercise is to calculate the first non-trivial correction in perturbation theory to the energies under an off-diagonal perturbation, H1 acting on those same states, psi 1, psi 2, psi 3, gives me back, let's say 0, epsilon, 0, negative epsilon, 0, negative epsilon, 0, epsilon, 0. Psi 1, psi 2, psi 3. And so we want to get the first or leading correction to the energies in perturbation theory. So let's start off at first order. As I mentioned this morning, the first order shift in these guys is 0. It's all completely trivial because this matrix has no diagonal element. So we see that, let's say, the shift of state 1 at first order is equal to the expectation value of the perturbation in that state. This matrix tells me what happens when I let H1 act on psi 1. I return back epsilon, but times psi 2. So this object gives me epsilon, psi 1, psi 2, and this object is 0. So what this is essentially telling me is that because this matrix, when H acts on psi 1, is off diagonal, it has no overlap with the state that it started off with, this expression is 0. So in the same way, all of them are 0. E1, E2, and E3 at first order in perturbation theory are all 0. So the exercise is to go to the first non-trivial order in perturbation theory, which is second order. At second order in perturbation theory, the second order shift to energy 1 is a sum over all other states. So this is a sum over all n not equal to 1. But not equal to 1 in this case just means that this is a sum over n equals 2 and 3. Those are the only non-trivial ones. You have the transition matrix element squared going to a state n by action of the Hamiltonian on the initial state 1. It's squared because you have 2 of them. And then you have an energy denominator, which is the energy you start off with, E1, minus the energy En that you go to. So in this case, if I start off in the state 1, when the Hamiltonian acts on the state 1, it only returns back state 2. Hamiltonian on state 1 gives me epsilon times psi 2. So for this reason, this matrix element is only non-zero for n equals 2. This is particularly simple because there's only one term. So only n equals 2 is non-zero. And in this case, the numerator is simply epsilon squared, and my denominator are the energies from the unperturbed Hamiltonian. The energy of state 1 was E, minus the energy of state 2 is negative E. So altogether, I get a correction of positive epsilon squared over 2E. This makes sense in second order perturbation theory because we get a positive shift of this energy E. This was the ceiling state, the highest energy state in the system. This receives an upward pressure from perturbation theory from all of the states below it. So one should always get a positive energy correction at second order to the ceiling state. Likewise, if I go to the second order shift of energy number 2, now I have a sum over all states that are not equal to number 2. So this is n equals 1 and 3. And Hamiltonian 2 squared over E2 minus En. Now, in this case, when Hamiltonian acts on state 2, I get 2 contributions. So I get something from psi 1 and something from psi 3. Both of them have the same value, negative epsilon, and then that gets squared. So I have 2 contributions. First, I have n equals 1. For n equals 1, I get epsilon squared upstairs. E2 has energy negative E, minus E1 is E. Now I have another contribution from n equals 3. This one is also epsilon squared, but the denominator is different. I have negative e minus negative 2e. So when I work this out, this first term is negative epsilon squared over 2e. This second one is positive epsilon squared over e. So altogether, I got a positive shift epsilon squared over 2e. Whereas the ceiling state always has to go up, the ground state always has to go down. States in the middle can go in either direction depending on which pressure is greater, above or below. In this case, the upward pressure from the state below, that is the state with negative 2e, was greater than the downward pressure from the state above. And that's exactly because this lower state differs only by e. The difference between this one and the upper state differs by 2e. So since these two states are closer in energy, this energy in second order in perturbation theory is more strongly repelled from below. So this overall ends up going up, and this positive correction wins out. The last one is the correction to energy 3 at second order. Here you have a sum over n equals 1 and 2. N Hamiltonian 3 squared over E3 minus n. In this case, there's only one non-zero overlap. So H1 on side 3 gives me epsilon times side 2, and that's it. So only n equals 2 contributes. And in this case, I get epsilon squared upstairs. Downstairs, the energy was negative 2e minus the energy of state 2 is negative e. So altogether here, I get a negative correction, epsilon squared over e. So the ground state goes down, and you see that this one is more strongly repelled than the others. It's downward repelled from the two states that are open. Okay, pretty straightforward. I think actually the phrasing of the problem asks you to find the overall energies to this accuracy. So strictly speaking, probably you should rewrite the final answer. Maybe I'll put it over here. You would say the energy of state 1 is equal to its original value, which is E, plus the correction epsilon squared over 2E. The energy of state number 2 is its original value, negative E. It also received the positive correction plus epsilon squared over 2E. And energy number 3 was negative 2E. This one receives a negative correction, epsilon squared over E. And all of these statements are valid up to higher orders in perturbation theory, which would be one further suppressed by the small number, which would go as epsilon cubed over E squared at most. Okay. For problem 16, a particle in a three-dimensional isotropic harmonic oscillator potential of frequency omega is perturbed by electromagnetic waves of different frequencies moving in different directions. So you have a 3D harmonic oscillator. If the combined effect from the interference pattern is the time-dependent Hamiltonian H1 of t is equal to the x operator, e to the I omega plus 2 little omega t, plus y operator, e to the minus I capital omega minus little omega times time, plus z operator, e to the I capital omega times time. With capital omega an arbitrary frequency. Then find the transition rates. To any excited state with quantum numbers nx, ny, and z. First order in perturbation here. Okay, so for the 3D harmonic oscillator, the energy of the excited states is E with quantum numbers nx, ny, and z, or nx plus ny plus nz plus 3/2 h bar omega. And recall that this just comes from writing the Hamiltonian h equals p vector squared over 2m plus 1/2 m omega r vector squared, and just separating all the components, that this is hx plus hy plus hz. 3 identical copies of the harmonic oscillator in x, y, and z, so you have 3 identical contributions to the energy. And x plus 1/2, and y plus 1/2, and z plus 1/2, giving you the total energy nx plus ny plus nz plus 3/2 h bar omega. Okay, so for time-dependent perturbation theory, the key here is to use Fermi's golden rule, which is that the initial to final transition rate is 2 pi over h bar, transition matrix element squared, times energy conserving delta function. E final minus E initial minus h bar omega, and this specifically corresponds if the overall potential has the time dependence e to the minus I omega t. So what we have here is a sum of 3 different contributions of exactly that form, each of which will lead to different final states, and each of which will have different energy conserving delta functions. So this is really sort of 3 independent contributions to the transition rate. So let's start off with that first one. For x e to the I omega plus 2 little omega times time. The transition matrix element that I want here is to some final state nx, ny, and z. X operator 0, 0, 0 is my initial state. And my time dependence here is e to the I big omega plus 2 little omega times time. So this operator is just a standard harmonic oscillator problem. This only affects x. It has nothing to do with y and z. So this is root h bar over 2m omega. This is the matrix element between an x, and y, and z of a plus a dagger. And this is a and a dagger specifically with respect to the harmonic oscillator in x, the x coordinate. So I'm going to put a little x down here. 0, 0, 0. This one is going to give me an energy conserving delta function of E final minus E initial. And I have plus I omega t here, so I get plus h bar big omega plus 2 h bar little omega for this particular time dependence. This matrix element is only non-zero when the creation operator acts on an x, and this just simply gives me delta nx1. Ny and nz are just spectators. They are still set equal to 0 because they are not affected by this operator. And y0 delta nz 0. So altogether, this one gives me a contribution to the transition rate. So this is rfi coming from the x term is 2 pi over h bar. I square this thing to get h bar over 2m omega. And then I have transition specifically to the state delta nx1, delta ny0, delta nz0. The original state that I started off with had energy E equals 3/2 h bar omega. This final state has nx increased by 1. So let's see. If the initial state was 3/2 h bar omega, I add 1 to it. This state has energy 5/2 h bar omega. This is true anytime I have this position operator raising one of the quantum numbers by 1. So it's no accident that this difference is 1 unit of h bar omega because I go from the ground state to one of the first excited states. This gives me overall the energy conserving delta function, delta of h bar little omega plus h bar big omega plus 2 h bar little omega. So at the end of the day, I simplify things a little bit and I get pi over m omega delta nx1, delta ny0, delta nz0. And then the energy conserving delta function is delta of h bar capital omega plus 3 h bar little omega. And if you really want, you can pull out the factor of h bar from the delta function and just write it in terms of the external frequency. Pi over m omega h bar, delta nx1, delta ny0, delta nz0, energy conserving delta function capital omega plus 3 little omega. So that's the first contribution. And we'll do almost identical things for the other two terms. For the y term, our final initial y term, I'm going to get 2 pi over h bar. I have a transition matrix element nx, ny, and z. This case, I'm keeping a y operator, 0, 0, 0, squared, times my energy conserving delta function is going to be E final minus E initial. And in this case, I have minus big omega minus little omega. So I'm going to get minus h bar big omega plus h bar little omega. In exactly the same way, this matrix element is going to be the same as it was before, except now it's going to raise ny by 1 unit. So what I'm going to get is 2 pi over h bar, same prefactor coming from the raising and lowering operators. H bar over 2m omega. Now I'm going to get something that says nx is still 0, and y has been raised to 1, and z is still 0. And if I've raised the energy by 1, then this energy difference is simply h bar omega. So my energy conserving delta function is delta of 2 h bar omega minus h bar big omega. And if you like, you can simplify this a little bit further to write it as pi over m omega h bar, delta nx 0, delta ny 1, delta nz 0 times energy conserving delta function, let's say omega minus 2 little omega. Or I use the symmetry of the delta function to flip the sign of the argument just for convenience. Okay, and again, not much else changes for the last term. That's just this guy. So I have our final initial z term is 2 pi over h bar, and x and y and z, z operator 0, 0, 0 squared. And now my energy conserving delta function is simply delta E final minus E initial plus h bar capital omega. Again, this is going to simply give me h bar over 2m omega. Now this is going to raise z by 1 unit. So I'm going to get delta and x 0, delta and y 0, delta and z 1. And the energy difference here is exactly 1 unit of h bar omega. So this is simply h bar little omega. My energy conserving delta function is h bar little omega plus h bar big omega. And once again, cleaning everything up, I simply get pi over m omega h bar, delta and x 0, delta and y 0, delta and z 1. Energy conserving delta function, let's say big omega plus little omega. So that's it. We've calculated all of the terms. If you like, we can add them all together and summarize. So overall, the transition rate to any allowed final state, all three of them have the same prefactor, pi over m omega h bar. So the transition rate is the same to all three possible final states. And I have simply a difference in the resonant frequency for each transition. So delta and x1, delta and y0, delta and z0. This transition came with the energy conserving delta function there, omega plus 3 little omega the second transition, which excites y from 0 to 1. Came with the energy conserving delta function capital omega minus 2 little omega. And the last transition to nz equals 1 had the energy conserving delta function big omega plus little omega. So this is my transition rate. There are 3 possible transitions that are going to be driven here, but they all are driven at different resonant frequencies. So if you have the frequency big omega equals negative 3 omega, you will excite this transition, which excites the state in X. If you had big omega equals positive 2 little omega, you would excite this transition in Y. And if you had big omega is negative little omega, then you would excite this transition in Z. 3 possible transitions taking place at different resonant frequencies. Okay, next problem, number 17. Calculate the differential scattering cross-section, d sigma d omega from the potential V of R equals V naught capital R over little r, 1 minus little r over big R times the theta function of big R minus little r, meaning that this is only non-zero if R is less than capital R. So the exercise is simply to plug into the Born approximation for the scattering amplitude and then into the cross-section. You are calculating this to first order imperturbation. The scattering amplitude f of q is minus m over 2 pi h bar squared Fourier transform integral d3r e to the minus I q vector dot r vector v of r. In this case, the potential is spherically symmetric. So if I write the integral in spherical coordinates, 2 pi h bar squared negative m. I have integral dr, 0 to infinity, times the measure of r squared. I have integral d cosine theta from negative 1 to positive 1. And I have integral d phi from 0 to 2 pi. My theta direction, I choose to reflect the orientation of r with respect to q. That's equivalent to defining the z-axis to point in the direction of q. So my Fourier phase is e to the minus I qr cosine theta, and the potential itself is v naught r over r 1 minus r over r times the theta function of r minus little r. So the phi integration is trivial. This one immediately gives me a factor of 2 pi. And my theta function of r just cuts off this integral to infinity at capital R. So if I simplify this, I get minus m times the constants v naught capital R over h bar squared. I have integral from 0 to capital R dr. I have 2 powers of r from the measure and 1 over r here inside the potential. So that simplifies to 1 power of r. And now I have the stuff that I need to take care of. Minus 1 to plus 1 d cosine theta e to the minus I qr cosine theta times 1 minus r over r. From the angular integration, when I integrate this thing over cosine theta, I get 1 over negative I q r times e to the minus I qr minus e to the plus I qr. So this takes care of the last angular integration, and I can simplify the expression. So f of q is equal to, let's see, I have negative m and 1 over negative I, so that is altogether negative im v naught capital R over h bar squared, and I'm left with my radial integral 0 to capital R d the r. Now this last factor of r here gets canceled by the 1 over r. I also have a 1 over q that comes out front, h bar squared q. And now I just have that polynomial factor 1 minus r over r times the difference in phases, e to the minus iqr minus e to the plus iqr. So there are various ways to do this integral. My instinct is to split up this second term and say this is a copy of the first one with q goes to minus q. So I'll write this as minus im v naught r over h bar squared q times integral 0 to capital R dr, 1 minus little r over big R, e to the minus iqr, minus a copy where q goes to negative. So if I do the integral once, I can just duplicate the answer and obtain the full expression. H bar squared q 0 to r. Yes, okay, good. So let's proceed by evaluating the integral. I have f of q is equal to minus im v naught r over h bar squared q. Integral 0 to r dr, 1 minus r over r, e to the minus iqr, minus q goes to negative q. So rather than trying to integrate the factor with the polynomial in it, I prefer to write little r here as something obtained by a differentiation by q. So I will take this and I will replace r, which I can get by taking a derivative with respect to q on that expression, and that's going to bring down minus ir. So if I multiply it by I, that can account for my factor of r. So I can write this as negative im v naught r over h bar squared q. The polynomial then comes outside, 1 minus I over r d dq, acting on just the exponential 0 to r dr, e to the minus I qr. And at the end of the day, I have to subtract q goes to minus q inside its bracket. This integral is an elementary one. This is 1 over minus iq, e to the minus iq capital R minus 1. So when I take this expression, the 1 is simple. This gives me I over q e to the minus iqr minus I over q. That's this factor times the 1. So, and then I have, let's see, I have minus I over minus I, so I get plus 1 over r times d dq of the product q to the minus 1 e to the minus iqr minus 1. Okay, so evaluating this, I have d dq of q to the minus 1 e to the minus iqr minus 1. If I differentiate the first term, I get minus q to the minus 2 e to the minus iqr minus 1. If I differentiate the second term, I get plus 1 over q times from inside, I bring down a factor of minus ir e to the I minus iqr. So filling in everything in brackets, I have f of q is minus im v naught r over h bar squared q. Inside the brackets, I have I over q e to the minus iqr minus I over q plus 1 over r times this stuff. So I have plus 1 over r q squared e to the minus iqr minus 1 minus ir over Q, and there was a 1 over R to go along with it, which cancels this one, e to the minus I QR. And then I have to subtract from this, Q goes to minus Q. Okay, so life is kind for once, and I simplify some of these terms, those pieces go. When I subtract Q goes to minus Q, all the pieces that are left give me, I have minus I over Q, and then I subtract Q goes to negative Q. So that's going to give me another copy of the same thing. So I get minus 2I over Q. This is 1 over R Q squared. For this one, when I subtract Q goes to minus Q, the first term is 1 over R Q squared e to the minus I QR. Then I subtract Q goes to minus Q, that's going to give me plus I QR. The last term here was minus 1 over R Q squared, and then I subtract Q goes to minus Q, but these are the same thing. So they cancel out. So it looks a bit messy, but things clean up a bit at the end of the day. Let me pull out this factor of RQ squared here. This combination, by the way, is negative 2I sine QR. So if I pull out the factors, I have minus IM V naught R over H bar squared Q. If I pull out an overall 1 over R Q squared, then this first term simply becomes minus 2I QR minus 2I sine QR. Let me check my sums here. Oh, I think I dropped the factor of I. I've got minus I in front, and then minus I here. Off by a sign somewhere. So I got this piece, there's that one, and oh, minus 1 over Q squared. I think that was it. This should have been minus 1 over Q squared from the beginning. Yes, this should have been minus 1 over Q squared. That was the mistake. Okay. There. That looks better, so that now this ends up becoming plus 2IQR. So at the end of the day, I get from my scattering amplitude f of Q. I can also pull out a factor of minus 2I here, or maybe even 2I. In that case, I get 2m v naught R cancels R over h bar squared Q cubed, and I pull out a factor of 2I, so I have sine QR minus QR. And then I simply square this to get the cross section. The sigma d omega is the scattering amplitude squared, so this is 4m squared v naught squared over h bar to the 4th q to the 6th. Sine QR minus capital R minus Q capital R squared. Yes. So working through the algebra can be a little bit messy, but there's no secret tricks here. Okay, almost done. We have now an exercise for finding the phase shift. Derive but do not solve algebraic equations which enforce the boundary conditions and relate them to the S-wave phase shift delta naught for a particle scattering on the delta shell potential V of R is V naught R delta of R minus R. So the point here is to derive the boundary conditions. Boundary conditions and relate to phase shift. So the delta shell potential is zero both inside and outside. It's only non-zero precisely at r equals r. So that means I can write down my wave function psi 0 of r is outside. I have a superposition of the Bessel function J0 of kr plus the Neumann function N0 of kr for r greater than capital R. Inside, I can only have the Bessel function because the Neumann function is singular at 0. So I can only have C0, J0 of kr for r less than capital R. And here, k is related to the energy for a free particle, h bar squared, k squared over 2m. So in this case, we have to enforce the boundary conditions at r equals capital R. The first boundary condition to enforce is continuity. If I simply take these expressions and set them equal to each other when r equals capital R, I get the first boundary condition. Now, one thing that I can do to make my life simpler is just plug in the specific form of the Bessel and Neumann functions for L equals 0. For L equals 0, these are particularly simple. They're just ordinary sine and cosine. So this is A naught sine kr over kr. And then there's a negative that goes with it for the Neumann function, cosine kr over kr for r greater than r. And then I simply have C naught sine kr over kr for r less than capital. So if I enforce continuity at r equals capital R, I simply set A naught sine k capital R over k capital R minus B naught cosine k capital R over k capital R equals C naught sine k capital R over k capital R. Obviously, the denominators trivially cancel across the board, and I simply get A naught sine kr minus B naught cosine kr equals C naught sine kr. So this is my first condition that corresponds to enforcing continuity. The second condition, which is less trivial to apply, would normally be differentiability. If you had a smooth wave function, you would require its first derivative to be continuous at the boundary. However, for a delta shell potential, the derivative is not continuous. The fact that you have a delta function causes a cusp discontinuity in the slope. We saw this last semester for scattering in one dimension. So the second criterion that we need to enforce is the specific magnitude of the cusp discontinuity. Discontinuity at r equals capital R. So the way to see this is to write down the Schrodinger equation and integrate over the singularity, just over an infinitesimal window that picks up the delta function. Integrate time-independent Schrodinger equation across the singularity. So if I write down the time-dependent Schrodinger equation in the radial direction, I get minus h bar squared over 2m d squared dr squared plus h bar squared L plus 1 over 2m r squared plus the potential, which is V naught r delta of r minus capital R. Normally, this radial equation acts on the radial probability amplitude, UL of r. But that radial probability amplitude is nothing more than r, the radius, times the wave function itself. So this is r times psi of r. Or r times big R of r, I think is what we called it before. Here we've already separated out the angular dependence, so we're only talking about the radial part. In this case, we're dealing with the L equals 0 part of the wave function. So for us, the centrifugal barrier does not contribute. It's just going. So what we have here then is a radial equation that tells us minus h bar squared over 2m second derivative d squared dr squared acting on r times psi 0 plus v naught r delta of r minus r times r psi 0 equals e times r times psi 0. And I want to take this expression, which is singular here at r equals capital R, and I want to integrate this thing just around that singularity. So let's integrate this from capital R minus epsilon to capital R plus epsilon. If I do this, then anything which is finite, in particular the energy term on the right-hand side, that's nice and smooth. In the limit when epsilon goes to 0, this piece is just 0. When I integrate this thing, the derivative here is a perfect differential. So I get a difference between this function evaluated at the upper limit and the lower limit. So I get minus h bar squared over 2m ddr of r psi naught evaluated at r plus epsilon. That's just inside this part of the wave function. Minus the derivative h bar squared over 2m ddr of r psi naught at r minus epsilon. That's just in this region of the wave function. When I integrate across, I get something finite from the delta function. So I get plus v naught r times the value of the wave function itself. R psi, I guess I can call this capital R psi of capital R. And this thing is equal to 0. So this equation determines the magnitude of my cusp discontinuity. So that second equation, let me move that v naught r times r psi to the right-hand side. And then I'll multiply by this coefficient. So a little bit cleaner way to write it is to say that the derivative of r psi 0 at r plus epsilon minus the derivative of r psi 0 at capital R minus epsilon is equal to, I move this to the right-hand side and I multiply by negative 2m over h bar squared. So altogether I get positive 2m v naught over h bar squared, let's see, times r squared psi of r. And now I can actually apply this condition to those wave functions. I take the derivative in this region just above r, and I take the derivative in this region just below r. So just above r, I get sine kr over k and cos kr over k. I take the derivative and I get a naught cosine k capital R plus b naught sine k capital R. That's the first term. Minus the derivative in the second region. This is simply c naught cosine k capital R. And what I get is 2m v naught over h bar squared r squared, and I can take either value of the wave function since we already enforced continuity for the value at r. So let me take the simple one here, which is c naught sine k capital R over k capital R. So this is my second algebraic condition. A naught, if you like, minus c naught cosine kr plus b naught sine kr equals one factor of r cancels. I get 2m v naught over h bar squared k times r c naught sine kr. And I think in the solutions online, I somehow managed to neglect keeping this wave function factor around to the right. We'll go back and fix that afterwards. All right, so this is the second condition, the much more complicated one. This is the value of the cusp discontinuity at R. The only other thing left to do is to relate these quantities to the S-wave phase shift. And that just involves taking the R goes to infinity asymptotics. We had psi of R was A naught sine KR over KR minus B naught cosine KR over KR for any R greater than R. If I take the R goes to infinity asymptotics, then this is supposed to map onto a plane wave with some coefficient D naught. It looks like the original plane wave with a phase shift plus delta 0 over KR. So we simply enforce the agreement of these two expressions as R goes to infinity. A naught sine KR over KR minus B naught cosine KR over KR equals D naught sine KR plus delta naught over KR. Now, obviously, the KRs downstairs are trivially removed, and it's easy to split up the sign here into addition of angles in trig. So I'll write this as D naught sine KR cosine delta naught plus D naught cosine KR sine delta naught. And then if I just match the coefficients of sine and cosine, I get A naught equals D naught cosine delta naught, and B naught equals negative D naught sine delta naught. These two expressions are written conveniently if you take the ratio so that you cancel out D, and then I get something like delta naught, let's say tan delta naught is negative B naught over A naught. So this is my condition number 3. This whole setup has basically reduced all of the boundary conditions down to a set of algebraic equations, something like this, and that enforce continuity, the cusp discontinuity of the slope, and the relation of those quantities to the phase shift. Given sufficient time and calculational resources, you could then solve this equation specifically and calculate exactly that value of the phase shift. Yes, I definitely dropped the wave function multiplying the delta function piece in the notes. So I will definitely go back and fix that. Okay. The last calculation on the sample exam is a variational estimate. So do a variational estimate of the ground state energy of an attractive Gaussian potential in 1 dimension. V of x is V naught e to the negative beta x squared using a trial wave function which is psi alpha of x, which is e to the minus 1/2 alpha x squared. Derive but do not solve an equation determining the value of alpha, which gives the best estimate of the ground state energy. So I'm asking you to derive an equation for alpha min. So the exercise is to set up the variational estimates. E of psi is integral dx from minus infinity to infinity. Psi star of x, the Hamiltonian is minus h bar squared over 2m d squared dx squared plus the potential, which is v naught e to the minus beta x squared times psi of x, divided by the denominator, which is integral from minus infinity to infinity dx psi of x squared. Okay, so of these things, the denominator is particularly simple. The denominator is integral minus infinity to infinity dx. I have two factors of e to the minus 1/2 alpha x squared. So this is e to the minus alpha x squared, and this is a standard Gaussian integral that everyone has memorized, whose value is pi over alpha. So this immediately I can plug back in. The other piece that I can do very quickly is the potential. The part which comes from an integral of the potential is integral minus infinity to infinity dx. I have v naught e to the minus alpha x squared from the wave function, e to the minus beta x squared from the potential. So this is v naught negative infinity to infinity dx, e to the minus alpha plus beta x squared. And this integral is again the same standard one, which is v naught times square root pi over the combined with alpha plus beta. The only one that's non-trivial to do is that first term, which is this derivative. So let's work that out carefully. So the kinetic energy piece is minus h bar squared over 2n, integral dx minus infinity to infinity. I have the wave function conjugate 1/2 alpha x squared, d squared dx squared, e to the minus 1/2 alpha x squared. So first I have to take the derivatives, and then I have to deal with the integral that's left. So I have two derivatives to take. If I take the first one, then I'm left with another derivative hanging around outside, and when I differentiate the exponential, I get an extra factor of minus alpha x, multiplying back the same Gaussian. Now if I take another derivative, I have one term that hits just the first piece, so I get minus alpha e to the minus 1/2 alpha x squared. And I've got a second term hitting the exponential, which again brings down another factor of alpha x squared, plus alpha squared x squared e to the minus 1/2 alpha x squared. So together these derivatives give me a polynomial piece, negative alpha plus alpha squared x squared e to the minus 1/2 alpha x squared. If I plug that back into this kinetic energy integral, I get negative h bar squared over 2m, integral dx from minus infinity to infinity, minus alpha plus alpha squared x squared e to the minus alpha x squared. So I have a Gaussian integral but multiplying a polynomial. My preferred way to handle this is to get this factor of x squared by differentiating with respect to alpha in the answer. So I'm going to take this piece and write x squared as what I get when I take d alpha of the Gaussian with a minus sign. That lets me pull the polynomial outside the integral and write it as minus h bar squared over 2m. Negative alpha now minus alpha squared d alpha of the Gaussian. Integral dx minus infinity to infinity e to the minus alpha x squared. This finally reduces the Gaussian down to the standard integral root pi over alpha again. And so what I get for the kinetic piece was minus h bar squared over 2m. Let me pull that square root of pi out front because that's not going to do anything. I have the root pi. I have negative alpha minus alpha squared d alpha, and all of this is acting over alpha to the minus 1/2. So obviously the piece with the constant in it just goes through. Square root pi, and so I get minus alpha to the 1/2 minus alpha squared. If I take a derivative of this thing, I get negative 1/2 alpha to the minus 3/2. So together this is negative alpha to the 1/2 plus 1/2. I've got alpha squared upstairs, alpha to the 3/2 downstairs. This is again alpha to the 1/2. So this nicely conspires to give me positive h bar squared over 4m square root of pi times alpha. Now I've computed all of the pieces, I can plug that back into my energy function. So my energy functional E of psi has now been reduced to a pure energy function. 1 over the denominator was square root alpha over pi times the kinetic piece, h bar squared over 4m square root pi alpha plus the potential piece. And the potential piece was plus v naught square root pi over alpha plus beta. So if I distribute everything out, the factors of pi cancel, and I get h bar squared over 4m alpha plus v naught square root alpha over alpha plus beta. So this is my energy function for a Gaussian of arbitrary width, and now I need to minimize this. Plus or minus? Oh, I think I didn't write down the minus sign from the beginning. It's supposed to be an attractive Gaussian with negative v naught. So this potential should always have been minus v naught. I think I may have dropped that minus sign when I first set it up. Okay, for an attractive Gaussian, this is what it is. Now that's good because this will have a minimum instead of a maximum. So let's find the minimum by setting dEv alpha equal to 0. The first term is simple. I get h bar squared over 4m. For the second term, I have two pieces. So if I differentiate the alpha to the 1/2, I get minus 1/2 v naught alpha to the minus 1/2 alpha plus beta to the minus 1/2. If I differentiate the denominator, I have, let's see, minus v naught alpha to the 1/2 times negative 1/2 alpha plus beta to the negative 3/2. So I get 0 is h bar squared over 4m. I have some factors in common here. I've got the 1/2 and the v naught. So let me write this as plus v naught over 2, and I'll pull out a common denominator. I've got 1 over alpha's square root and 1 over alpha plus beta to the 3/2. So let me pull out, let's say, alpha to the 1/2, alpha plus beta to the 3/2 as an overall common denominator. What I'm left with here is a factor of, let's see, alpha plus beta from the first term with a minus sign. So this is negative alpha minus beta. And then the second term is a positive, and I pulled this out, and I have an overall factor of alpha. So this cleans up just a little bit. The alphas cancel, and I get a negative beta. So my expression is 0 equals h bar squared over 4m minus beta v naught over 2 alpha to the 1/2 alpha plus beta to the 3/2. And this is good enough for an answer. You've simplified it down to an algebraic equation, not straightforward to solve this, involving 4 different powers of alpha. But you have successfully boiled it down to an algebraic equation. So this was what I asked you to find. Okay, and that's it. We've now gone through all of the calculations on the sample exam. So good luck preparing. Let me know if you have any questions. As I said before, the sample exam is representative of the content that will be on the final exam. I will do a much better job of calibrating the time on the real final exam. The stuff that's been on here has not necessarily been calibrated the last 120 minutes. So if you have any questions, let me know, and be sure that you submit the midterm by Friday and any corrections that you have before the end of the semester. Thanks very much.